G'day, Michael here. I'm doing this video because, well, something that's quite exciting for me, and that is I'm playing with this idea of a deflection-based tyre. So instead of pneumatics, like where it's inflated, you've got deflection. I mean, I've seen this, people have been playing with this elsewhere, it's not my invention, but obviously working out a design that does something that you need it to do, like a certain, how can I say, a certain weight loading, have a certain behaviour, you know, it's something that I'm quite curious, because I have things like wheelbarrows and trolleys and things that I use outside, and the tyres, you know, they deflate and they don't do what they're supposed to do. Yeah, so I thought I'd make my own one of these. This is a scale model just to test an idea. Let's just see what it does. So with a bit of pressure on it, it deflects a little bit. I don't know how well that shows up. But this one's a little bit stronger than I want it to be. I want it to probably deflect about twice as much as that. Okay, so let's put that back up again. Sorry about the shakes. Alright, so that's this design. Now I created that with VariCAD, which is a really good all-round sort of modelling program. It's available for Linux and Windows. It is a commercial package, so it costs money, but it's not online, so your designs are on your machine. So I'm a bit reluctant to do, people promote online drawing applications, but this works offline. So if I'm away, out of an internet area, I've got the ability to use the program wherever it actually is. Alright, so let's get VariCAD happening. Anyhow, I designed this with VariCAD, but what I very quickly discovered, sorry about this, I designed this with VariCAD, but what I very quickly discovered was that it became unbearably slow to drive. This camera right again. Alright, so if I was to, I don't know, create a block, yeah, let's do that. That's not what I want. So let's just create a block, put it, I don't know, there randomly. Okay, so that's in place. So it's partially overlapping. So it's interlapping or overlapping. So let's add those two parts together so it makes it part of that other design. So I'll add that to that. Cool. Now that worked reasonably well, but that was only a cube, a cubic shape interacting with a few facets there. When you're working on, okay, one of these curve components, and you want to like splice it in, like you have like a union, or if you want to use intersection where to see where two parts like occupy the same space, we have to generate these spokes, I had to create like a donut that these items would also be in the same space. If I had a look at, maybe, can I edit one of these entities? If I pick on that, you'll see that that came from a larger ring. That's, I kind of cheated that way. But so that I got it to only include the bit that I want in the middle there and not all this other space, this other volume of it, I created a donut in the center here, and where the two both exist, it keeps intact. So I'll just undo that. So where both this center, where this center donut exists, and that spoke ring exists, it keeps the part. But naturally, that's a lot of work for the computer to work out all these little facets, because I guess it's easy to underestimate how many little corners, like vertexes. If you have a look at, is there a way I can get access to these? What have I got in the slicer? Original. Okay, if you look here, where are you? Put you on every desktop and follow me around. Okay, so go to Cruise the Slicer. You can see here there's triangles, and the whole shape, regardless of these radii, they're all triangles. So if I can zoom in enough, you can see you've got little facets here, and every little, even rectangular piece is actually a rectangle that's divided into two triangles. So there's squillions, like really heaps of facets. We've got shells. Well, there's 482,000, well, nearly 483,000 triangles in that. That's like 500,000 triangles that the computer's got to keep track of every corner, and how any other piece might interact with it. So there's a huge amount of data that the computer's got to work its way through and work out intersections to see what overlaps what, and where two planes meet, it has to generate a whole lot of new vertices. So yeah, there's a lot of work for the computer to generate these sorts of shapes. And so as a result, using a pointy clicky type program, like if using a pointy clicky type program, often manipulations will take it ages. Now let's just undo that. There we go. So the program is just busy as hell. Let's just see how busy it is. We'll get that on this desktop, and it's just busy. I mean, in this case, it's one CPU core working its heart out. And so when you're doing things on the CAD program, you're just basically sitting there for a minute or two, each one of these sorts of modifications. And so you get very frustrated with the fact that you can't get the job done. Anyhow, I wasn't happy with this design, so I wanted to modify it. So with these sort of pointy clicky GUI based programs, it became like a monster to try and manage. This is just best redesigned, not go through undo and retry or do things a bit differently. It's easy to just forget it, start from scratch. But I remember playing around with it, OpenSCAD, with a couple of designs that I downloaded from Thingiverse, like gears and of all things orthotics. And I never really got my head into how it ticks, but this design motivated me to have a go at understanding how it works. So let's just have a look at what I did do. Now this is a newer design based on what I learned. Where are we? Okay, based on what I learned from making this, I wanted to make a fewer spokes, and I've also done something a bit interesting with creating these spokes. Are now like they're sort of twisted in opposing axes, so you end up with like a chevron section. How does it? You see, maybe there. It's hard to see. There's like a chevron shape there, and how I achieved that was half the design is like twisted one way, and the other half is a mirror image of that first half. You can see this line here, both X and Y axis, is 0 on the Z, so half the wheel is above 0 and half it's below 0. So it's very, it's kind of a cheats way of doing it. I just use the mirror function. Okay, so what is the code like? I might manipulate this a bit. Okay, so now you can see every line here is actually a line of text rather than having the return. This is the sum total of the actual execution part with the OpenSCAD, because I've created like modules that do the grinding of the various parts of that. Each half is generated by this module called spokes, and that's the code that's involved with that. And then there's a module donut which generates the absolute shape. Like, see how the corners here are radiused and it's basically a ring. Well, that donut is created in this section here. The spokes generates that section of all these spoke lines, and then does the twisted extrusion to give us that kind of a chevron effect section. So one up, one down, and so one sort of clockwise twisted, and the other one's anti-clockwise twisted. Right, but when that's all called, it's called by this. So breaking it into modules keeps the bit you try to figure out smaller and smaller, so it's easier to sort of create, but it's also easier to debug if there's a flaw. If you're looking in a smaller and smaller part, it's easy to spot, oh, I didn't use the right syntax, or I used the wrong variable, or I wasn't thinking about that the right way. So by making modules like that, it's the easiest way to manage it. Okay, so this looks like a real headful, but surprisingly, from zero, having no idea how to use OpenSCAD, to this, it only took me a few hours. So I'm very pleased with this, because this design took me about an hour anyway. So learning OpenSCAD's basics, certainly enough to get this design happening, didn't actually take me that long. I've had some experience writing code before, but not this particular code. But if you look at it, the language is quite, human readable. It's not like some obscure code. And these parameters up the top here, I've set them up. They're just variables. So you give them whatever name suits your mind. So it's a quick process to set up these values. And then you've got your execution part of it. So yeah, it was quite quick for me to do that. Now the downside I find with OpenSCAD is, well, when you get it to execute a design change, it uses only one CPU core, but that, if you think about it, that's necessary, because it has to do this first, that next, that next, that next, etc. So it has to be sequential rather than be able to parallelize out a heap of work. Like the slicing programs can go, let's have a go at slicing 5 layers in a row and use up 5 cores or 12 cores or whatever you've got at hand. So using, say, Prusa Slicer, when you hit slice, it just saturates the CPU usage and gets the job done ASAP. Whereas this OpenSCAD is single CPU core working its heart out, and it can't parallelize into GPU because it's having to read your code and execute it as you've asked. So I get it why it does that, but it's a limitation. So we've got a lot more horsepower available to us than OpenSCAD lets you use. So it takes this design takes like about 15 minutes to crunch out on my machine. It's nominally 3.5 gigahertz per core. I think it bumps that up to maybe 3.8 or 4. It's a Xeon based Dell T5500. So it's got a nice number of cores. I haven't enabled hyperthreading. It has 12 real cores and potentially 24 threads if I enable hyperthreading. I found for most tasks it's slightly better performance because there's enough cores by just leaving hyperthreading off. But some programs benefit from hyperthreading. So it depends what you're going to do. I will also give a small warning here. Do not do this on a laptop on a regular basis. You'll really shorten the life of your laptop. Alright, so how does this actually work, this OpenSCAD? Now let's play with that. I'll just close that, do that again. Close without saving. Well, what I found very useful on the OpenSCAD was its cheat sheet. I'll just close all that. Help. Cheat sheet. Very, very useful sort of a setup. Where'd that end up? Over here. Okay, I'll drag that out. Which desktop were we? Okay, we'll just get that. See you over there. Alright. So you've got these from what I can tell, pretty much all the instructions. So there's not actually that much of a language set. Like, it's not like 10,000 different keywords or whatever. It's pretty simple. You're basically working with primitives, like you might be making a cylinder, a cube, maybe a pyramid type function or whatever. But basically that's all you're making. You're making objects, and then you have them intersect with each other or use one as a tool to cut a hole in the other, that kind of thing. And the Boolean operations is what they're called, where you're sort of adding or subtracting logically. Union is the default behavior, and that's when you put two objects in the same space or interacting somehow, they'll just be combined as one sort of double object, whatever it is. Difference is, let's just have a look at a difference example. There we go. Difference is actually where you're using the second part as a tool to cut a hole in the first. And intersection is obviously where two parts overlap. The bit that's left of their overlapping is what's kept. So they've got good examples there. Very quickly accessible, easily understood. Now let's go back to difference. This example here, let's open a new window. I'll get that. No, not that. This guy. I'll put this on top so it doesn't keep on disappearing behind. I might reduce the size of that window CAD. Okay, so here's this lot. So we can drag this bit of code, copy and paste over here. We press F6 and it crunches it out and gives us a bling. Anyhow, that's what that's done. The downside of doing things this way, where you define everything just as the numbers within your instruction, is you've got to actually manipulate each line that it's on. The advantage of creating modules and creating these variables is you can use a variable and then it's just carried through wherever that name exists. And also you can divide a variable by 2 on the fly, or whatever you need to do to manipulate that variable. So going back to our little copy-paste example, what I would do, let's just analyse what this does by changing some numbers. I'll move that aside a little bit. Let's just change the radius, because that's what that is, the radius of this first cylinder. I'll make it, I don't know, 2. F6. And now it's twice the size. Now, it's got that hole cut into it, and that's created by a cylinder, this bottom cylinder, which has been rotated. The logic of OpenSCAD is, here's what we're going to do to whatever's coming. It's not, we've got this stuff and now let's manipulate it. It's, here's a manipulation of whatever's coming. So here, the first instruction here is difference, which means it's going to use one to take away the other. And what are we going to do? What's our first shape? Is a cylinder. What are we going to use to take away from that? We're going to have a rotate of something. So we're going to have something yet to come, which is going to be rotated, which is going to be a cylinder of this size. So your brain might want to go, I've got to do a cylinder first, rotate it next, have another cylinder to compare it to, and then work out the difference. Well, this is kind of, the logic is reversed. It was reversed certainly to my thinking, and that's what took me a little while to get that in my head. So you're saying what you're about to do, then you go off and give it what it's got to work with, rather than the other way around. Okay, so let's just modify that to being only, actually I'll pull out the cylinder so you see what that cylinder looks like with only the cylinder being generated. So I'll copy it and put it outside this bracket, so it's outside this function. There goes my compressor. Okay. I might change its length, because I can't see it, to say 7, so we can see it. Let's do that again. Okay, so that's our cylinder. I might change this one to 7 as well. Cylinder. So we're talking about the same thing. Now you can't actually see that cylinder. We'll do the next thing, and that is rotate it. Okay, so now I've got a rotate command, which, like I said, we're going to say what we're going to do, and that is we're going to rotate something, and here's what we're going to rotate, the cylinder. Okay, so F6. This is a workshop. We have a compressor. All right. So now you can see it's produced that. But what if we change the rotation angle? Let's do something different. Let's make that, I don't know, 80 degrees. We'll have a different angle. There we go. So if we do the same to the one above, we'll have an angled hole. And I might just comment this out so we don't see it. So that's how, if you want to temporarily disable a line, you can just make it a comment. So now you can see our original cylinder with the hole cut in it. It's got the hole at an angle. Alright, but the cylinders, everything's got its own little magic. There's more depth to these instructions than it's just a cylinder. We can use this string FN, which is facet number. At the moment it's set to 100. So if you look at this, it uses 100 facets to go around the cylinder. Now, that was on the first cylinder. The second cylinder, if we make that say 6, we'll end up with a hexagon, which is pretty cool. So if you need to have like a hexagonal hole cut through something, we have a hexagon. So that's pretty cool. But let's say you wanted this apex up here rather than there. Well, we'd have to rotate it 30 degrees in the y-axis. So this is rotation about the x-axis, rotation about the y-axis, rotation about the z-axis. So let's do that. Okay, so you can see we've just managed to get at basically 10 degrees off right angle. We've got a hexagonal hole. The hexagonal hole is nominally a radius of 0.9. That's from the center point of the hexagon to the peak. And it's been rotated at 30 degrees so as to have an apex top and bottom. We could have some other location based on that rotation. So that's pretty simple, right? Now if we want to rotate it around the z-axis, like we don't want it coming square out this way, we want it a little bit around, let's make it go around, let's say 45, that'll do, 45. Hopefully that'll behave itself, there we go. And you can see that comes out at 45 instead of the other way. So we'll put our original cylinder back in so you can see what we had before. We had a circular cylinder coming out that way, but when we started the design it was already 90 degrees off the website, so that's what their original was more like. So the number of facets can be used to create all sorts of things. Now let's just make that only 4 facets, so we end up with a rectangular item. See, we've got a square, so it's pretty cool. There's a lot of different things you can do. If we wanted to rotate that, maybe 45, so it's got flat facets, that kind of thing. So you can do all sorts of groovy things with it. And that could have been defined as a cubic shape too, so whatever you want to do. Now I use an interesting thing here, I'll let you look it up, Minkowski, which is super cool. It is a way of adding one shape to another in a strange... Just look up Minkowski. It's really cool. That's very cool. Minkowski. I was very much impressed by that tool. Actually, they might have a good one here. No, not there. Missed it. That one. Minkowski. There we go. It is super cool. So, to make a rectangle with a rounded corner, I'll just zoom in a bit on that. You generate a cylinder like that, and a cube, and then the sum total of the two spaces, like one added to the other going around, produces this. So that's a very cool way of getting a rectangle with rounded corners. Basically define a rectangle bit and a circle bit, and it adds the two together to make the one below it. Very cool, and that's in fact what I used for this donut. Oh, excuse me, I'll move that aside. That's what I used for the donut shape that is made here. So you might just make one more donut. Oh, and it'll take too long to generate. This takes about 20 minutes to crunch through. It's a big deal. Yeah, no, I can't use that. Although I could cut out the spokes. And a mirror. And the union. I think that's right. And the intersection. That work? Hello? Okay, so that shape there was created by doing this square here with a circle. I might cut out the rotate. Try that. So there we have the rectangle with rounded corners. It had to be translated away from 0, so I'll undo that. So this is the Minkowski by itself. And if we take away the Minkowski instruction, so we just see the circle and the square. You see the circle, and you can't see the circle because the square's in the way. That's the circle. So you can see by tweaking the instructions, you build. Oh, go away, fly. There's our donut. So this is used as a primitive to later on with using the intersection function to define the whole volume that the tyre is allowed to take. So regardless of what we create otherwise, we're only going to keep the bit that fits inside this donut. Alright, so if we don't have that, union spokes, might just do spokes. And I won't do the donut. I'll turn off the donut. Is it going to work? I think that's right. Okay, so there's the set of spokes, which is 1/2 of them. This is the bit above. Okay. So now I'll do the mirror of those spokes, the one that goes below. I've got a syntax error. Oh, that's what I got wrong. As you come here, you can see I've got the end bracket. It tells you which bracket it belongs to. So you're able to keep track of opening brackets and closing brackets. Crunching, crunching, crunching. Now, because it's got a mirror, it's got to do a lot of work. So, oh, come on, you can do it. As you can see, the time starts expanding out here. This machine is using 18.1 gigabytes of 47.2 gigabytes. So you can see that the RAM in your machine is definitely being used pretty heavily here. I am doing a screen recording, which also costs power, as in CPU power. And so this is where you start hitting like speed limits on OpenSCAD, because it takes a long time to generate, which is what I alluded to earlier. But having said that, what you can do is create a number of, like once you know your design is actually functionally correct, so it's not going to fail, you can launch, I think I might even have one open, here we go, you can launch a script. So these are all my SCAD files, and a couple of STLs, and I ran a little while ago, OpenSCAD yada yada, that's the output I called it, from whatever design, and it'll sit there and crunch in the background whatever part that is. Now let's just 20, 15. Yep. So if you create various different designs, you can, let's do tire1.scad test.scad. OpenSCAD. Just call it video. So I've just run a command line that's done the script. Obviously not much of a design. Okay. Let's go back to the original. See what that actually is. At that design. do.stl is what was created by that script. I don't even know what I had here. Oh, that's it there. Okay, so this is an example of that cylinder with a hexagon section put through it. So, like I said, if you have a design that's sorted, that you know works reliably, you can play with different values and run it from a command line. So, if you've got multiple CPU cores and you've got a design that works and you want a whole lot of different options, just edit them, save them with the different parameters and give them a name that's unique, and you can launch them from the command line. So that's a way of getting lots of tasks done on a multi-CPU machine pretty quickly. But I mean, they all take their 20 minutes or whatever it is, but they can run in parallel. So the other advantage I've found with, pardon me, running these scripts, because I only use one CPU core, they don't really hold up your machine. With a slicer, if we go back to, I might delete that, we add that that guy again. As soon as I go to slice it, so that's the design. It's doing the slicing right now, and the CPU usage goes through the roof. Hopefully the video will hold together. It's a lot of work for the machine to do right now. This takes a long time. It's 14:06 right now, so it would have been 14:05-ish probably. No, 14:06 would have been about right. 40 seconds, 40 seconds, yep. Okay, so this job's now done. So this is what I was waiting for before. You've got the twist rotate both ways, so you've got both sides of that. But you can see they've just made a flat surface, and that's why I needed the donut. So I'll just move that aside. So we needed to join those two halves together. So it's a union of the spokes function plus a mirrored spokes function. That's one up, one down. And then we've got to make the original donut, but run an intersection of the two so that we end up with that donut with radius corners, which is what we had in the first place. That's going to take ages to do, so I'm not even going to run that here for the video. Let's go back to our slicer. Still waiting for it to slice. It's working pretty hard. That'll be a while. I can't remember how long the slicing took, but it took some time. Alright, so what's the result of all of that? Let's just see what I've got going on another screen here. Videos, no, that's not it. That one, here we go. So let's open that with, no, oh, Gcode, so we've got to go to Gcode, so there we go. Cricket. I'll open it with a Gcode viewer. Oh boy, the machine's busy. to see how hot this thing's getting. '80s and '90s. Fans running pretty hard. It would have been running barely inaudible, a barely audible sort of thing. Now I can start to hear the fans working. This is why I say don't use a laptop for this if you're going to do any quantity of it. And you can see the RAM I'm going through right now. It's pretty hard on the machine. We're approaching 4,000 RPM with the processor fan. .27 gigabytes of RAM used. Here's our Gcode Viewer. The Gcode Viewer is actually quite a nice way of looking at your print paths at the Gcode level. I do find it quite cool actually. Very nice tool. So if you want to have a look at G-codes before we print them, so you can remember what the design is if you lost a little bit, you can use YAGV, which is yet another Gcode viewer, to view those things. I'm not sure what's available on Windows, but this is a good one on Linux. And it's a synaptic install, so you don't have to go looking for any software. Right, where are we at? Slicer seems to be finished. It is. It's still generating G-code, but it has done actual slicing. So move that aside. Now this is all parametrically designed, so you can see the power of using, say, OpenSCAD to create your design. And yeah, I guess that's pretty much all that I have to show in this program. But so you can see, by using OpenSCAD, if you can work out how to make a design like this in an instruction set, if you want to change a parameter, you can easily change it and have the machine do the work of it. I can see myself, if I had to, maybe now that this recipe has been worked out, maybe generating 100 designs on this machine in a day, whereas using, say, a typical visual CAD program, maybe 5 or 10. Yes, that's 20 times as productive, provided it's a recipe that you're producing. If you can't kind of make a recipe as to how the design's made, well, maybe not so useful. But yeah, be aware of how good OpenSCAD is actually to use, and it's actually quite easy. Yeah. Well, I guess that's it. Feel free to like, share, subscribe, ask a question, leave a comment. Bye for now.